So we're going to start with this sheet, and I want you to take this and fold it in half, hamburger style, like so. When I'm at the board, my back is in the way. When I use the document camera, my hands are in the way the whole time. I just can't win here. But so once you have it folded, then you're going to open it up and fold the sides into the middle where that line is. Both sides. And then you're going to need you're going to need a pair of scissors. Don't cut until I give you instructions though, because oh my gosh, somebody's going to cut this thing completely in half and it's going to drive me nuts. So I didn't put lines on the outside, because if I put lines on the outside and on the inside, they never match up when you copy them. But we're just going to random here. There's horizontal lines on the inside, but if you cut all the way across, it cuts it in one big strip. That makes absolutely no sense. So you're going to cut on this line right here, just to the first, so that it looks like this when you're done. You see, I just cut along there to that first crease. To the first crease, but you got to look at the inside part so you can see the lines so you're not cutting through words. All right. Does everybody understand? Check your neighbor. Ask for assistance if you need assistance. Yeah, just keep it in mind. Well, you know, I try. Oh, that's because I share my foldables. All right, so while you're cutting, let me tell you a little about what we're doing. On your calendar, it said ready, and there was like a little exponent on the T. So really there's two T's, so maybe that makes it ratty. I don't know. RAT2EY is also what some people call it, and that always bothered me. I couldn't figure out why. It always made me think of Ratatouille, like the movie, and I didn't get why it was called that, why they were pronouncing it. But I finally got it because it's way more obvious. That's probably why I wasn't understanding. And I'll show you. So it's like rat. Well, we're going to write it again, and then I'll show you. But is everybody here? Good. Okay. So but it's not just. But I'm going to call it RATY, even if it's supposed to be ratty or something else. But RATY's fine because it's an acronym. It doesn't matter if you pronounce it right. So PPD, we're adding a little extra thing to our acronyms because we have to find all of this stuff. And this is going to give us everything we need to find all in one place with one little acronym here to be able to graph our rationals. So not new information in this foldable, just organizing all the stuff we already know. So this is actually called PPD RATY. So in this first box on the outside, all capital RA, capital T, the second power EY. So I asked somebody who wasn't even really familiar with this. I was like, I don't get the RAT2EY part. And then they were like, RAT2EY? I'm like, oh, that makes sense. I don't know, but so whatever. But RATY's fine too. Whatever. So PPD RATY. Okay. Because again, RAT2EY may sound just like mispronouncing it. But this is our little acronym that's going to help us. So if we open this up, this is our the P and PD part. So we're looking for, does it have a parent? Like a parent function. Is there a parent function? Because some of them will, but not all of them. So our parent functions for rationals could look like this. Right? That one was f of x would equal what? 1 over x. Okay, that's our reciprocal function. Another one that is not new to you, but we did talk about it when we talked about parent functions, is one that's like this. So really the only difference between these two is that the left-hand part got reflected up across the x-axis because all of your y values are positive. This is not an absolute value thing that is making that happen. What else could happen with x to make all the y positive? Squared. This is 1 over x squared, or the reciprocal squared function. Okay. So, does it have a parent? If the answer is yes, so if so, just do transformations. Okay, just do transformations. That's all you have to do. There's nothing fancy about it, but not all of our rationals are going to have parent functions, so they're not all going to be able to just be done with transformations. Okay, so the PD part of that, what do you think PD stands for? Could stand for police department, yes, but in this case, it would be point discontinuity would make way more sense, right? So point, and then discontinuity is a long word for that little blank, but I couldn't make it any bigger. I made it as big as I possibly could, so just write the word small. Discontinuity, and I didn't want to abbreviate it right here. I don't care if we abbreviate other places, but point discontinuity, long word for a little blank. So our point, again, this isn't new. We've done it for a few times already, and it wasn't new to you then. But these have to be factor or factors containing x that is common to the numerator and denominator. So that's your PPD part. Does it have a parent function? If so, we're going to be able to just do transformations. We're not going to have to look at anything weird happening. We should be familiar with that. And then point discontinuity is the next thing that we look for. Okay, everybody good with all that? All right, so then our next little box here, starting with the radii, with our R. R is for roots. What's another word for roots? Zero. Okay. And solutions, yes. But I guess radii sounded better than zadie or sadie. I don't know. So roots, the same thing though. All right, so our roots are the x-intercepts which are the zeros of what part of the rational? I mean, it is the zeros of the function itself, but so is this found before or after reducing? Before. No. After. What's the only thing we do before? Domain. Domain's the only thing you do before. Okay, so found after reducing. And we know how to find x-intercepts. I hope we should. All righty. So then A. A stands for asymptotes. In this case, this A only stands, it's only talking about the vertical asymptotes. We will get to the other ones soon, but vertical asymptotes here. So our vertical asymptotes come from a unique factor containing x, and that factor has to be where? The denominator, good. And then, as we know, our asymptotes are a line or lines determined by the zeros of what? The denominator. Okay, zeros of the denominator. All right, so we got to have our roots, we have to have our asymptotes. Then our T stands for 2. And there are 2 things that start with T along with this. That's why there's 2 of them. So, do any of the factors of R or A, meaning any factors in the numerator or denominator, have an even exponent? So it's not just do we have an even exponent in our function, but the factors themselves, okay? Like the multiplicity part of this. Whether it's 2, 4, 6, 8, those are all even numbers. So if the factor itself has an even exponent in the numerator, then that gives me tangency, just like it did for polynomials. So it could look like this. Now that's just part of it. That doesn't mean that that's the whole function. It would be tangent to the x-axis. Basically, that's where your bounce comes from, right? If you have a factor that has an even exponent in the denominator, that is where you get togetherness. Togetherness. So here's what the togetherness part of that means. Say that I have this asymptote here, so the togetherness could look like this, or I could have this. Okay, so that's like your little x and y axis. My pink line is my asymptote, and those are like parts of the function, not the whole thing, just parts of it. And then this is what would not be togetherness, right? So the togetherness tells us what's happening on either side of the asymptote. So they're either on either side both going to infinity or both going to negative infinity. If I have that even exponent in the denominator, it will not be opposite like this. If there is no even exponent in the denominator, then it will be opposite. Okay, so line through it like that. Okay, everybody okay with that? All right, so that's your tangency and togetherness that we have to look for so we know what to do with these graphs. Okay, let me zoom back out a little bit. So then our E stands for end behavior. So that means we are looking for when x, okay, that pen is not working there. When x approaches infinity, then f of x approaches something, right? But we're talking at the very ends, right? Not middle behavior, end behavior. Gives us two different things. This is where our horizontal and our slant asymptotes come into play. Our vertical asymptote doesn't affect end behavior. That's more the middle behavior. End behavior here, horizontal asymptote is going to be HA. Right? If it's top heavy, what's true about my horizontal asymptote? There's none, right? There's none. What happens when it's bottom heavy? Y equals 0. Then when it's tied in degree, y equals the ratio of what coefficients of the numerator and denominator? Any of them? The leading coefficients. Good. The leading coefficients. Then our slant asymptote, another word for slant is oblique. So that's your SA there. That's when the degree of the numerator is what? 1 degree higher. Okay, so I'm going to put one more. 1 degree higher is a little bit more official, but it doesn't fit in the blank as well. Degree of the numerator is 1 more than the degree of the denominator. So when that happens, we divide and do what with the remainder? What do we do with the remainder? Big and Can I have both a horizontal and a slant asymptote? No, because they're dealing with in behavior. If you have one, you do not have the other. It doesn't work that way. All right. So then the y. Y stands for your y, what? Intercepts. Okay. Your y is your y-intercept. And just like every y-intercept you have found ever before, you substitute 0 in for x and solve for y. And these are always written as what? Ordered pair. So written as an ordered pair. So if you can find PPD radi, you have everything you need to be able to graph your rational function. So when this gets glued into your ISN, it doesn't get glued in sideways like we've been doing everything else. It should be like old school ISN way. On the back, I'm going to write this is going on page 63. So whether you glue it or tape it, just, this whole back right here can be just flat down so it looks like this in your ISN. And since it's going on page 63 should be a left-hand page. Your odd number is always on the left. So if that's not what's happening, then skip a page because I want this on the left and then the next thing that we're doing on the right. Okay, we good? All right, so let's grab the other piece of paper. You can just go ahead and fold it in half. And this is going on 64 and we're done. So we're going to do a few quick graphs, which should be the same kind of things you've graphed before. We're going to get into some more interesting, more complicated ones, but these are really basic today. So in order to begin this, just like every rational we've done so far, we have to start by factoring. So in the numerator, I have x plus 2. In the denominator, I'm going to have x minus 3 times x plus 2. Right? And then, is anything going to cancel out? Yes. The x plus 2 is going to cancel out, right? Which tells me I have a whole with an x value of -2, right? Then my reduced function is just going to be, x minus 3? 1 over x minus 3, yes. So 1 over x minus 3. So does this thing have a parent function? Yes, okay. This does have a parent function, okay, and the parent function looks like this, right? This is your reciprocal, so that's the parent function, right? Which means we can use transformations for this, but we still have to fill in everything else that goes along with this. So my whole is at the x value is at -2. Now that I have this, I can substitute it in. What's the y value? -1/5. Okay. Then, what are the roots? It's the empty set. We don't have any, so it looks like this, right? Do I have any vertical asymptotes? Yes. X equals 3. Any tangency or togetherness? Do I have a factor that has an even exponent in the numerator or denominator? No, so there's none of this. Do I have a horizontal asymptote? It's bottom heavy, so what is it? Y equals 0. Since I have a horizontal asymptote, can I have a slant asymptote? No, so this is none. What is my y-intercept? Zero, -1/3. Good. That was not a difficult question, by the way. I'm just saying. All right. When I look at this as a parent function, what kind of transformations are happening? Translation, you're going to go right 3, right? And this parent function has an asymptote at x equals 0 and y equals 0, right? And so what we did with transformations is our asymptotes had to move also, right? So if I'm going to translate to the right 3, this x equals 0 goes to the right 3. That's where that comes from, right? So that's where that comes from. And then we don't have a vertical translation, so that y equals 0 is still y equals 0 there, right? And this will help us with some points. All right, so let's go down to our graph here. We're going to ignore this number line. We'll talk about that in just a minute. But I need to graph all of these things that I have so far. I have a hole at -2, -1/5. So -2, -1/5 will be right about there. Make a hole. Right. Then I don't have any roots to graph because I have that asymptote there. I have a vertical asymptote at x equals 3. So I'm going to come put that in there. And then I have a horizontal asymptote at y equals 0. Even when they are the axes, you have to draw them in. I realize on these graphs, the axes are kind of dark. I tried to change that. It would not let me change that for, I don't know why. But but you have to be obvious that you've actually drawn that in and you just didn't just use the axis there. And then we have a y-intercept at 0, -1/3. Okay, so all those things have to be on there no matter what. Then, because we are using this as a parent function, because I only have 2 points here and some asymptotes, I really don't know where anything else is right now, but my anchor points, remember we're at 1, 1 and -1, -1. So if I have this anchor point at 1, 1 and I translate to the right 3, I just go 1, 2, 3, there's a point right there. Then I had -1, -1, I translate to the right 3, here's my other point. Those 4 points and those 2 asymptotes are a non-negotiable. If you do not have all of those things on the graph, along with what else we're about to do, you are not getting credit for it. You just slopping curves on there because you think you know about where it is not okay. These help you get the actual accuracy and the shape of what's going on. All right, so then, because I do know what the parent function looks like, right? We had it drawn up there. Then I know what it's supposed to look like, and I can start over here. Don't draw straight through the hole because that's the whole point of that, right? That just, the whole point, I know. I'm a comedian, I didn't even know it, but then we keep going, make sure you hit both of those points, which I almost didn't there. Oh, my board is bouncing. When my board's bouncing, I can't draw. Stop bouncing. Okay. It's still bouncing. Okay. I'm just going to make this point bigger. They're bouncing upstairs, or I don't know what they're doing. They don't have to do much, but it makes the floor bounce, makes this bounce. So yours shouldn't be as wonky as that, but I kind of give up. And then this looks like this. Yeah. If it's on paper, it's a little bit easier, but when my board's bouncing, I can't get the points right. All right, we good with that? Easy enough? That should be along the same lines as a rational that you've graphed in the past. It's easy, yes. All right, next page. Or flip it over. So once again, I'm going to start by factoring. My numerator is going to give me x minus 2 times x plus 1 over x minus 2. Am I going to be able to reduce? Yes, which means I have a hole with an x value of 2. My reduced function, f of x equals x plus 1. Does this have a parent? Yes, we have a parent function here. Okay, it does have a parent. What is the parent? Linear. So it looks like this, right? All right, so that's nice. Lines are easy. Then my y value for my hole is what? 3. What are my roots? -1. Do I have any vertical asymptotes? No. So there's none. Any tangency or togetherness? No. So none. Horizontal asymptote? No. Slant asymptote? No. So none and none. Y-intercept? 0, 0? 0, 1. Yes. So I have all these pieces. Now I'm going to take all these pieces and I'm going to plot what I have so far on my graph. So I have a hole, because I can't see mine now, at 2, 3. There's the hole. Okay, what's the question about? What are we confused about? Ask me a question. What are you talking about? You found out, but that's okay. What were you thinking though? Because you might be the only one. No, it's okay that you were talking about it. I just because by what the definition we're using, it says that there has to be an x in the denominator. And so yes, the numerator, because the numerator would be degree 1, the denominator would be degree 0, right? So the numerator is higher in degree, and actually, depending on how you look at it, lines really do have slant asymptotes. They're just themselves. We just weren't going to get into that right now. So it kind of does have one, and it's itself, but we'll get to that later. Right now, we're going to go with none. Okay. So I have 2, 3, and then my root is at -1. And my y-intercept is at 0, 1. Okay, so my parent function is a line. These are the 3 points that I have to have plotted from all that stuff up there. Do I need to graph anything else? As far as points are, I need to graph a line, but do I need to plot any more points? No. So use your ID, makes a great straight edge, and we're just going to draw that in. And this is what it looks like. Okay. All right, are we all good? Yes? Any questions? Awesome. All right, so we're ignoring the number line. We're going to look at it on this next one. All right, so we are going to factor again. So this will give me x plus 4 times x minus 3 over x minus 3 times x plus 2. All right, so I'm going to get to reduce, which means I have a hole with an x value of 3. You're not always going to get to reduce, by the way. There's not going to be holes in everything we do. That's just these 3 examples happen to have that. And so then I have f of x is equal to x plus 4 over x plus 2. So then what is my y value for this hole? 7 over 5. Does this have a parent? No. Both of those parent functions have a 1 in the numerator, or a constant. There's not a variable in the numerator. So if I have a variable left in the numerator, it is not a parent function, okay, which means we don't really know what's going to happen at this point. Okay, so then I find everything else. What's my roots? -4. My vertical asymptote, x equals -2. Is there any tangency or togetherness? No, because I don't have those exponents there. Do I have a horizontal asymptote? Y equals 1, good, because they're tied in degree. And then that means there's none for the slant asymptote. What's my y-intercept? 0, 2. Okay. Everybody good with that so far? Okay, so because it doesn't have a parent, I don't necessarily know what it's going to look like, right? So when there is no parent function, I do have to look at the number line. And when we did rational inequalities, I'm just going to rewrite this because I can't see mine. X plus 4 over x plus 2. When we did rational inequalities, what all did we have to plot on the number line? The zeros and the vertical asymptotes. So basically the things that you're getting from your R and your A, right? Those have to go on the number line. So that means I have -4 and -2. And I'm not even putting points on here. I don't care about open and closed circles here because I'm not technically solving an inequality. I'm using the number line idea, which you're going to use a lot in calculus, but the number line idea, but I'm not actually plotting points. But I'm still doing everything else the same. So now I'm going to look at, if I choose something over here that's less than -4, like -5. When I substitute it in here, it's going to give me negative over negative, which means overall it's positive. Then between here, I'll use -3. So that would give me positive over negative, which would be negative overall. And then over here, I could use 0, so be positive, positive, and be positive overall. Okay? We all good so far? Now, this This is your 0 where it actually hits the axis, right? So there's an actual point here on my axis. And then this is where my asymptote is, right? And if we look at, you don't always have to draw this on a number line. I just want to make sure you understand what's happening here. If I look at the number line as the x-axis, though, and then we're going to shade. So you're just going to shade with your pencil, because this is where it makes it useful for us. Since from negative infinity to negative 4, it's positive, I'm shading above the x-axis right there. Okay, so you can just shade that in with your pencil. And then between negative 4 and negative 2, it's negative. So it looks like this. And then from negative 2 to infinity, it's all positive. So this is just telling you where the y values are. Sometimes that's all you care about when you're actually applying these things, just because that's when you're looking at velocity, is it moving left or right, or those sorts of things, what's happening there. That's going to help us graph what we need to graph, okay? So let's go ahead, and on our graph, we are going to put in the everything we can graph. We've got a hole at 3 7/5. So 7/5 is like 1 2/5. So 1, oops, let me get my pen. I'll go to 1, 2, 3, and then 1 2/5 could be like right there, so there's a hole. Then I have a root at negative 4, so I have a point on my x-axis there. I have a vertical asymptote at negative 2. Okay. And then I have a horizontal asymptote at y equals 1. And y-intercept at 0, 2. So again, these points that I have right here, non-negotiables. Since there isn't a parent function, I don't know, there's nothing I can do to do transformations. This is kind of all I have to go by, and this number line. Sometimes this number line may not help me as much as it does other times, but sometimes it's where I get most of my information. Here's what this tells me, is that between negative infinity, from negative infinity to negative 4, my graph is positive. So I have this asymptote, which means it's going to be hugging this asymptote, and it's positive all the way until it gets to negative 4, right? So it's going to come in and look something like that. Then from negative 4 to negative 2, my y values are negative. Well, here's my negative 4, negative 2 is the asymptote, so it's going to go down like this. And because it's negative here and then positive here, they're opposite because there is no togetherness, right? If there was togetherness, it would come back from right here. So it's positive for all the rest of the time. This is my my horizontal asymptote. As far as I know, it doesn't cross it, because remember, you can cross horizontal asymptotes sometimes. What I do know is it's always positive, so it's not going to dip down below here, and I'm going to assume it doesn't dip down below my asymptote, so it's going to look like this. And this is the best we can do with the information that we have. Make sure there's arrows on everything, that you've got these points plotted that need to be, and you have the holes in the right place. Just slopping some nasty curve down somewhere ain't going to get you any credit. Okay? We good? Any questions? Alrighty, so you can go ahead and glue both of those in. I'm not giving you an assignment today because I wasn't even sure if we would finish these notes.